So now it's time to begin, so I'll start my presentation. So thank you everyone for attending this presentation. I will talk about software pipelining support for AArch64 in LLVM. I'm a Ryota from Fujitsu Limited. We are now developing Fujitsu Monaca, which is an AArch64 processor, and we are now developing toolchain that targets the Fujitsu Monaca, and this is a part of it. So this is an overview of this presentation. MachinePipeliner is an LLVM optimization path that is work for software pipelining. We implemented AArch64 support and some improvements for MachinePipeliner. Our works are submitted to LLVM as several patches. As a result, there are programs that become faster on Neoverse V1. But we believe that we can make more improvements for MachinePipeliner. So we Fujitsu will continue contributing to LLVM. So at first, I will talk the background. Software pipelining is an algorithm that aims to optimize loops. We believe that software pipelining is valuable for processors because of following two reasons. The first one is that these days processors are adapted for not only for embedded systems, other than for example, data center and HPC areas. Neoverse series is one of them. And the second reason is that software pipelining is an effective optimization algorithm for loops with chains of instructions, which is typically in HPC applications. In addition, software pipelining has proven track records with AArch64FX, which is an processor we developed. Moreover, performance improvements can be expected for processors without simultaneous multithreadings. And Neoverse V1 and with doesn't equip Neoverse with is not equipped with SMT. In addition, software pipelining is also effective for Fujitsu Monaca, which is a processor we are developing, as I mentioned at the beginning. So from here, I will show a brief example of how software pipelining works. Please to make its simplicity, please consider in order processor that has one issue, one load store, and one other units, and the latencies are shown as here. Then consider executing this target code on this processor. This code is very simple loop. This here shows which instruction is issued at each cycle when we execute it. When we execute this target code on this processor. Left one shows where we execute this target code on the same order as it is, and right one shows where the software pipelining is applied to this target code. Each iteration, each box is colored by iteration, and the white box show means pipeline stalls. As you can see, if we don't apply software pipelining, there are pipeline stalls, and it takes 6 cycles to execute one iteration. On the other hand, if we applied software pipelining to the code, there are no pipeline stalls, and it takes 4 cycles to execute one iteration. then let me introduce a term, initiation interval, which is an important notion in software pipelining. Initiation interval means the cycles between successive iterations, and initiation interval is ultimately equals to how many cycles it takes to execute one iteration. So in software pipelining, smaller initiation interval is generally better. So in this case, the 4 is the best initiation interval, and actually there are no pipeline stalls, and it achieves the best schedules. This is how to realize the previous this schedule, and please note that this is at source code level, and actually software pipelining is applied to assembly, or in LLVM, a wrapper of assembly called MachineIR. This is the original code, and this is what is software pipelining is applied. As you can see, the most important part of this code is the body of the loop called a kernel. As you can see, in the loop body, iterations overlaps, and as a result, it can achieve this schedule. In this case, three iterations overlaps. As you can see, this is I-2, and this is I, and this addition is the iteration of I-1. Please note that we have to, in this case, we have to insert additional moves, and these moves can degrade performance. I will talk about how to address this issue later. So this concludes the example of software pipelining, and from now, I will talk about software pipelining in LLVM. As I said at the beginning, in LLVM, MachinePipeliner is optimization path that is responsible for software pipelining. MachinePipeliner consists of roughly 3 phases. The first phase is the analysis of the loop, and MachinePipeliner at first analyze the target loop and then construct a graph called data dependence graph. And this graph contains information about the dependencies between instructions and the latency of instruction and so on. In the next phase, MachinePipeliner schedule instruction sequence based on this graph and generate instruction sequence. Finally, MachinePipeliner expand the scheduled instruction sequence and then generate actual code. Here is our main contributions for MachinePipeliner. We submitted some patches, including minor bug fixes, but these first 3 patches are our main contributions. So from here, I will talk about the details of these patches. Please note that MachinePipeliner requires a scheduling model for each processor. However, we can use the same one that is machine scheduler utilized. So we don't have to implement additional one if machine scheduler if it is already implemented. So at first, I will talk about AArch64 support for MachinePipeliner. This is analysis part for MachinePipeliner, and to make MachinePipeliner available, we have to implement a function, analyzed for pipelining, that is analyzes and identify instructions that modifies loop counter variable or instruction that checks loop conditions. Due to the nature of these instructions are architecture specific, we have to implement these functions for each processors, and in this case, we have to implement this for AArch64. In fact, in this function, we search for instruction of BCC or instructions that modifies condition flags and then branching. These bottom two functions are utilized to another patch we are developing now. I will talk about this patch later. So the minimum requirement one is analyzed loop for pipelining. The next one is more general patch that aims to improve scheduling algorithm. As I talked at the beginning, initiation interval in software pipelining is equals to how many cycles it takes to execute one iteration. So generally, smaller initiation interval is better. However, in some cases, smaller initiation interval doesn't necessarily to be best one, because smaller initiation interval tends to generate additional register space fields and they can degrade performance. So in this patch, we introduce a new mechanism that rejects schedule that has high register pressure, so that it seems to generate additional register spaces and fields. The register pressure means the number of variables alive at a program point. This figure shows example that the minimum initiation interval is not the best. This is the comparison of execution time, and this is number of iterations per iteration. So MachinePipeliner basically doesn't modify the original instructions. The difference of the number of instructions is occurred by the difference of numbers of register spaces and fields. So as you can see, if we adopt a minimum schedulable initiation interval, then too many register spaces and fields are generated, and as a result, it doesn't show best performance. The final one is expansion algorithm we are developing now, called modular variable expansion. As I also said at the beginning, software pipelining sometimes insert additional moves into the loop body. This is because we have to hold values across iterations, and there are no mechanisms such as register window. Modular variable expansion addresses this issue by unloading the loop kernel. So as here, in modular variable expansion, loop unloading works like register naming. So I don't explain the details of this code, but if you observe this carefully, I think you can understand how unloading works. So this concludes the details of our patches, and from here I'll talk about performance improvements we observed by software pipelining. At first, I will show environments, we used Graviton 3. So the CPU core is Neoverse V1. And please note that we only used one core and one thread, so it means that we don't consider parallel executions for now. So from here, I will show two cases we observed that and shows that software pipelining is variable. The first case is a simple loop that has long dependence chains. And by using this code, we compared the throughput between out-of-order only and out-of-order plus software pipelining. And this graph shows the throughput while increasing the length of these instruction chains. And because we used Neoverse V1, and the equal instruction of Neoverse V1 is 2, and throughput is 2. If this is executed in order processor, the maximum throughput will become 0.5, and if we used out-of-order processor, then the maximum throughput will be 2. And as this graph shows, out-of-order works fine if the chain is enough short. However, if the chain gets longer, then throughput goes down. On the other hand, if we apply the software pipelining, the throughput is stable and is near to the ideal throughput. This result shows that there are cases that can be covered, that cannot be covered out-of-order only. However, that can be covered by software pipelining plus out-of-order. The next case is a benchmark application. We used ExamineMD, which is one of the ECP proxy applications, and the application of molecular dynamics. This is a code fragment of this application, and this loop is a hotspot. This loop accounts for about 50% of total execution time. And this is a result. So as you can see, software pipelining reduces execution time with a hotspot loop by 6.7%. It is 3.6% overall. This result shows that there are any practical applications that is software pipelining is variable. Okay, so finally, I will talk some future works. We believe that there are still improvements that can be made against MachinePipeliner. These are the example we think that we want to work on, and I think the first two items are most important one. The first one is providing better user interface like pragma. And the second one is improving data dependence analysis of the target loops, especially for memory dependencies. So we will keep contributing to LLVM to enhance MachinePipeliner. And we are happy if someone is interested in, if you're interested in developing MachinePipeliner with us. Acknowledge this presentation is based on results subsidized by the New Energy and Industrial Technology Development Organization. So that's all of for my presentation. Thank you for your listening. And any questions?
Hi, this is great work. Thank you. You mentioned adding pragmas. Do you think source code annotation is probably where we want to make use of this? And have we considered profile guided optimization as another way of guiding when to apply it and presumably for setting some of the tunables for how it applies?
I want to make sure that my understanding is correct in your question. Your question is about how to give the way to which loop is applicable by the software pipeline. And if we give the way of pragma, the user do not have now user do not have the way of which loop should be targeted. So of course, as you said, one thing is PTO, profile guided optimizers, good way of telling the users. And other cases, so I didn't come up with the way of that's sorry, I didn't. But PGO, of course, profiler report is very usable, and if we're reading profiler, and you can find the most cost that is very high cost in their programs, and if the loop has is similar type of targeting we mentioned here was so that it has very long chain of instructions, or it has many instructions, and or some we can observe some recurrences in the loops. So I think it's practically we can find the loops by reporting bets. I don't come up so far. I didn't come up with any other better way. So.
Thank you. Obviously, this is all kind of obvious future work to make sure that this is used in as many places as possible.
Yeah, thank you. It's a good discussion point, I think. Yeah.
So to me, it looks very similar to a more complex loop and rolling. So my question is, how this play with the current loop and rolling strategies, and if you think you can move toward make this more generic and not AArch64 specific paths, and if it's gonna help other targets or a more generic framework to loop and rolling more with more performance and more opportunities to optimizations.
Do you mean that loop and rolling increases the opportunities that can be applied software pipelining? Like, do you mean? Yeah. So I think loop and rolling sometimes loop and rolling may increase the opportunities, but it is difficult to answer to say that that loop and rolling works. Loop and rolling works beneficial for software pipelining or not, because it depends on the case. But also, I think it is necessary to that user controls disable, enabling or disabling software loop and rolling and software pipelining. I think does this answer your question? Thank you.
Any other questions? Thank you.
Oh, thank you.